multiverse, the idea that the universe is constantly splitting into parallel copies of itself, appeals to atheists and determinists alike. It offers a philosophical way out of the anthropic question: why does the universe seem uniquely suitable to our existence? It lets us know that the universe is not random, but that nothing is predestined to happen, even our existence. The problem with it is that it fails Occam's razor and rests on the most tenuous physical arguments. It tells us that not only are there an infinite number of alternate realities out there, but that this must be so because it is the only way to explain quantum theory coherently. The latter statement is hardly true, and the strawman argument that its only rival is something called wavefunction collapse is also false. The anthropic principle, meanwhile, that the early universe actually produced an infinite variety of universes, mostly empty, and ours just happened to be the one suited to our existence, is a Bayesian argument. Bayesian arguments are expressions of what we don't know, not scientific theories. They are hypotheses based on how we think the universe ought to work. We don't know why the universe has the properties it does suitable to the formation of galaxies, stars, and planets. To say we evolved on planet Earth and not a lifeless moon because of the anthropic principle makes sense, but only because we know that such moons exist. To say that the universe is one of many parallel ones is just one of many possible explanations. Being confined to this point in time and space in a potentially infinite universe, where we have only been observing its expansion for the last 100 years, we can hardly make such bold claims. The answer is neither we are special nor many universes. It is, we don't know. The multiverse, or many worlds. Interpretation of quantum theory is a specific version of the age-old philosophical idea of multiple realities. Introduced in 1957 by Hugh Everett III, a student of two titans of American quantum physics, Wigner and Wheeler, the multiverse hypothesis challenged the Copenhagen interpretation, a revisionist strawman for single-universe interpretations of quantum theory that appeared in the 1930s. Both of these and other interpretations of quantum theory had to be introduced to solve a conundrum. What happens when we make observations of quantum phenomena? The most famous example of this problem appearing is in the double-slit experiment. In that experiment, you have something like a laser that shoots light at two narrow, closely spaced slits in a barrier. On the other side of the barrier, you have a sensitive light detector. Now, the question the double-slit experiment is designed to answer is this: is light made of particles or continuous waves? If particles, then we should be able to fire individual particles at the barrier one at a time, and they should appear on the detector as a blob. If waves, then our laser light will travel through both slits at once and create a wave interference pattern. That is, the single light wave traveling through both slits will become two waves that can cancel and reinforce one another. So, here are the two options. If light is made of particles and each particle can only go through one or the other slit, then we expect to see the single slit pattern. If waves, then the double slit pattern. If you actually perform this experiment, you find that you get the double slit pattern all the time, no matter how little light you send through, so that suggests that light is a wave. But you also get it from sending individual particles through one at a time and watching each dot appear. It seems like light is both. But it turns out that depending on how you perform the experiment, you can rule the wave part out. When you try to detect light traveling through each slit individually, rather than collectively, you find that the light only travels through one or the other slit. As soon as you are able to distinguish the path of individual light particles, they behave like particles and not waves, and you get a blob. It seems like how we measure it affects what we see. In the 1920s and 30s, through a lot of back and forth between scientists, quantum theory solved this problem by suggesting that the observation of the light packets, called light quanta or photons, caused the experimental apparatus to interact with the light's internal state to produce some outcome that depended on the setup of the light quanta and the apparatus as a whole. This solution, which grew out of work by Danish physicist Niels Bohr, Heisenberg, and others, became known as the Copenhagen interpretation. This interpretation would later be presented by its detractors as wavefunction collapse, in the sense that the interaction with the apparatus causes the light's wave function to collapse into a particle, meaning that how we measure things fundamentally alters reality. The Copenhagen interpretation as wave function collapse was largely a 1950s invention by those like Everett and David Bohm, whom we will get to later, and others who sought to challenge it. If it corresponded to any interpretation, it would be that of Heisenberg. not Bohr. It has become a modern revisionist myth that wave function collapse was the orthodoxy of the 1930s quantum theorists. It was not. In fact, Bohr would have denied the wave function collapses at all because, for him, the wave function was a mathematical convenience that didn't really exist. After all, it was complex-valued and thus had imaginary numbers in it. As a positivist, Stephen Hawking agreed with this interpretation. And no quantum experiment has ever measured a wave directly, only particles with wave-like properties. Bohr's philosophy, called complementarity, was more like the theory of relativity in that he considered the way you observed reality to have an effect on what you measure. That did not change reality itself. Rather, the indeterminate and mutually excluding nature of the quantum theory required that experiments could not always agree on reality. That was a scientific fact, not a philosophical desire. Many physicists, notably Albert Einstein, strongly disliked Bohr's and Heisenberg's interpretation because it suggested that particles do not have a definite classical state. They preferred a theory that said that experiments are simply unable to measure that state. The state must be hidden. Positivists said, so what? There is nothing beyond what we measure. Subjectivists said, so what? There is no reality independent of ourselves. Bohr was accused of being both of these, but what he actually said was, the whole situation in atomic physics deprives of all meaning such inherent attributes as the idealization of classical physics would ascribe to such objects. In other words, classical physics is an idealization of reality, and you cannot assume that particles inherently have a classical state. In fact, quantum physics suggests that they do not. Contrary to Einstein, Bohr contended, the experiment and the atom, or particle, were always one system, and you could not talk about the particle as having its own independent state, apart from the observer, any more than Einstein's notions of time and distance could be separated from an observer in motion. The only difference is that Bohr didn't propose what the actual state might be, as Einstein did for relativity using four-dimensional mathematics. Later detractors reinterpreted Bohr's philosophy to mean that part of the wave function vanished when an experiment was done. Reality was altered by observation. This falsely suggested that Bohr believed in the wave function in the first place, but helped their case. Let's talk about the wave function because this is what leads to the MWI. You see, the wave function is a probability field as well as a wave. Actually, the normalized square magnitude is, but we won't go into the signal aspects. It not only represents the presence or absence of light, as when it impacts a detector, it also represents the likelihood that you would, if you look, find a light particle. But if you are only producing one photon at a time, and you look all through the wave for that photon, you will only find it in one location with some probability. You will not find more than one. So that means that somehow the rest of the wave simply vanished when you looked. So wave function collapse is really wave disappearance. This is what motivated Hugh Everett III to pursue an alternative line of reasoning. He proposed that the act of observation does alter reality, but it does not cause the wave function to collapse. Instead, it causes the universe to split into copies of itself, one for each potential outcome of the observation. Thus, the wave function spreads across multiple universes, each with its own observation, including its own separate copies of the scientists observing the outcome. Once the split occurs, each scientist is not aware of the other copies, so it looks like a collapse has occurred. Physicists at the time scoffed at Everett's MWI theory. Indeed, when Everett tried to explain his theory to Bohr at a meeting in Denmark, Bohr thought it was crazy. It did exactly what people later accused Bohr of doing, which he did not do, and claimed that measurement changes reality. Everett left academia to pursue a career in military research. Quantum interpretation theories at the time were a quaint sideshow in the quest to develop theories of space, time, and matter anyway. While Everett was pursuing his doctoral research, physicists were developing quantum field theory, Yang-Mills gauge theory, and quantum electrodynamics, all of which went on to explain the nature of matter as observed in particle accelerators smashing atoms to bits. What was actually going on wasn't that important, as long as you could calculate the probable outcomes, and quantum theory already solved that. It was only later, in the 1970s and 80s, when quantum decoherence, quantum information theory, and quantum computing were introduced that the problem of interpretation reared its head again. Quantum computing promised to be able to solve computing problems faster than before, and even to solve unsolvable computer science problems. These were things that the father of computer science, Alan Turing, would have thought impossible for computers to do. The question arose, where was all this extra computing power coming from? And the answer was suggested, particularly by MWI proponent David Deutsch. Why in parallel universes, of course? Since then, physicists, particularly those who grew up after the completion of the standard model of quantum physics, have increasingly sided with MWI over what they think is Copenhagen. It's surprising it has taken this long, given that wave function collapse was invented to fail. The problem is that while MWI solved the wave function vanishing issue in a unique and perfectly mathematically reasonable way, it introduced the idea that the act of observation changes reality. This violates a principle that has been a part of classical physics for centuries: realism. Realism is the idea that the universe has a definite objective state, independent of those observing it. Albert Einstein was strongly in favor of realism. A universe that is subject to our whims as to what and how we observe things is the antithesis of realism. We also know that quantum theory is compatible with realism, provided you assume that all particles have definite positions that we cannot observe. That is, you assume that the universe has a wave function that we know about, but also a hidden register of where all the particles are. When we make an observation of a particle, we observe some combination of the hidden state with the wave function. For example, we can observe both wave and particle when we do the double-slit experiment, but detect one photon at a time. In this case, we see both individual photons appear and the wave interference pattern because the wave function directs the hidden particle states, and vice versa. We just don't see through which slit the photons traveled. Thus, observing the path of the photon is mutually exclusive with observing the shape of the wave function. It is just a choice that we make of what to observe. Yet, the universe's reality does not change because of how we chose to look at it. Known as Bohmian mechanics after David Bohm, who introduced the idea in 1952, a generalization of de Broglie's pilot wave theory from the 1920s, it is yet another interpretation of quantum theory, one that predates MWI. Unlike the other interpretations, some of the math is actually different, but provides the same predictions. It introduces something called the guiding function, Q, that evolves the positions of all particles in the universe at the same time, with hidden but instantaneous communication between them. In the double-slit experiment, unlike the multiverse, Bohmian mechanics says the photon goes through one slit or the other, not both, but that the wave function guides it into a wave interference pattern anyway. When you try to observe which slit it went through, you are interfering with the wave function and particle, and so you no longer get the pattern. It is very straightforward. It challenges Bohr's interpretation in that it suggests that particles do have an idealized classical state through the guiding function. That state, however, evolves non-locally, because it doesn't obey the speed of light. So it also challenges Einstein. Far from refuting Bohr, it upholds his interpretation on the whole because it says that experimenters are just viewing different aspects of reality through their experimental setups, not changing it. How they look at reality changes how they see it, but the underlying state is definite. While experiments destroy or alter the state of the particles under observation, they do not fundamentally change what is real for the observer. That is relativism, not subjectivism. We don't even know answers to questions like, what really happened at the Big Bang, what is time, and what is beyond the observable universe. We don't know what happens inside black hole singularities where new laws of physics may exist. Do the same laws of physics apply in the parts of the universe we can't see? We don't even have the knowledge to say such a thing. While we have discovered in the past 100 years that the universe is vast with countless stars and planets, it may be vaster still, and yet still be one universe. Thank you for watching. See you soon in the next video.